Welcome to the Foundry by Forge College. I'm thrilled to have you here for this explainer on Merkle trees in blockchain workflows. Today, we're bridging the gap between abstract cryptography, which, let's be honest, usually puts people to sleep, and real-world system architecture. We're going to look at how these complex algorithms actually power the decentralized networks we use every single day. And we'll break it all down with a really cool engineering-style schematic approach.
Okay, here's our schematic overview for today. We'll cover the data weight problem, the block header blueprint, our crate and catalog analogy, light client verification, and finally, the power of batching. Let's dive right in.
Section 1. The data weight problem, moving from math to machine. Now this builds directly on our previous explainer, constructing and verifying Merkle proofs. In that one, you rolled up your sleeves, you paired sibling hashes, and you hashed them repeatedly until you got a single root. You learned the math. But now, we've got to talk about the why. Why do we do all this hashing in the first place? Well, to understand that, we have to look at the massive data weight problem inherent in blockchains.
So imagine a full node. It's basically a massive sweating server in a data center somewhere, exhaustingly downloading terabytes of data, processing every single transaction, and hoarding every single block body. It does all the heavy lifting, and frankly, it looks totally exhausted. Now contrast that with a light client. Think of a breezy, nimble mobile phone sitting on a beach sipping a piña colada. It operates on highly constrained devices with limited bandwidth and storage. It has absolutely zero intention of downloading the whole blockchain. It only wants to fetch what is strictly necessary to verify a specific transaction. The entire goal of this math is to let that mobile phone stay right there on the beach, fully trusting the network without ever doing the sweaty server's job.
Moving to Section 2. The block header blueprint. Tiny but mighty.
This incredibly tiny but mighty blueprint perfectly illustrates the separation of powers in our machine. Just look at this schematic breakdown. We have three main artifacts. First up, the block header. It contains the Merkle root, a timestamp, and consensus fields. And what does it prove? It proves the commitment to the block data and its exact position in the chain. Second, the Merkle proof. This contains your sibling hashes and the path, proving the membership of a specific leaf, like your transaction, in the tree. And finally, the light client. It holds the headers and the proofs, allowing it to verify the authenticity of those headers and the correctness of the data inclusion. This is exactly how we decouple heavy data from lightweight verification. You don't need the whole block, guys. You literally just need the header and a tiny proof.
Section 3. The crate and catalog analogy. A mental model to keep things grounded.
I know cryptography can feel a bit dry. So imagine a vast library where individual transactions are sealed pages inside boxes. These boxes are then packed tightly into crates. Two adjacent boxes are sealed into a crate, and its label is the combined hash of their contents. These crates pair up to form even larger crates, and this repeats all the way up until one final massive crate has a single label written on it. That final label, that's the Merkle root. It acts as a master catalog entry. It represents the exact contents of every single page inside that entire library. If a sneaky person slips in and changes even a single comma on one page in one box at the very bottom, the final label on the top crate changes completely and unpredictably.
So, let's do a quick mental practice run using this blueprint to verify a page. You have your transaction, the leaf, and a couple of crate labels, which are your sibling hashes. Step 1. You compute the hash of your leaf and the first sibling to get H1. Step 2. You compute the hash of H1 and the second sibling to get H2. Step 3. You simply follow that chain of custody, write up the crate labels, and compare your final hash, H2, to the supplied Merkle root, the master catalog entry. If they match, you know exactly where your page is in the library without having to crack open a single other box. Just remember to watch out for ordering sensitivity. Concatenating the leaf and sibling in the wrong order is like putting your shoes on before your socks. Your verification is absolutely going to fail.
Which brings us to Section 4, light client duty, trust versus math.
A light client actually has two very distinct jobs here. Responsibility 1 is the authenticity of the header. The client has to look at the consensus rules, like proof of work difficulty or chain length, to trust that the header actually belongs to the real blockchain. Responsibility 2 is the correctness of inclusion. This is the math part, where it runs the cryptographic checks using the Merkle proof we just talked about. So, here is the absolutely crucial rule. Do not conflate the two. Proving a piece of data is mathematically in a tree doesn't prove that the tree is actually part of the official accepted blockchain. You need both the consensus trust and the cryptographic proof to be completely secure.
But what happens when our nimble light client on the beach is suddenly bombarded with requests? I mean, what if a smart contract needs to verify dozens or even hundreds of transactions from the exact same block all at once?
That takes us to Section 5, the power of batching. Optimizing the engine. If we stick to symbol-proof verification for hundreds of items, we end up doing the exact same hashing math over and over and over for paths that share the exact same branches. It causes massive, scaling, redundant hashing and creates these really bloated data transmission sizes. It's incredibly painfully inefficient at scale. Batch verification, though, completely changes the game. By aggregating common pathwork, we can compute those shared intermediate nodes just once and reuse them across multiple proofs.
The benefits here are massive. Batching drastically reduces the total number of hashing operations and significantly shrinks the size of the proofs transmitted over the network. But as we know in engineering, optimization isn't free. Saving network traffic and processing power introduces a new trade-off: intense bookkeeping complexity. The verifier client has to take on the strict, meticulous job of identifying exactly which nodes are shared without making a single mistake. It's basically like doing your taxes. One misplaced receipt, or in this case, one misplaced node, and the whole thing gets audited and fails. If the bookkeeping is off, you simply won't be able to reconstruct the exact route, and the entire batch verification collapses.
Let's wrap up the workflow. To summarize our blueprint today, Merkle roots serve as those compact master catalog commitments inside block headers. Light clients elegantly combine these authenticated headers with small inclusion proofs to verify data without downloading the whole chain. This strict separation of duties is exactly what enables trust-minimized verification. And finally, when scale is needed, batching saves a tremendous amount of work, but it requires very careful management. So as you move forward in your learning journey with other programs and courses, I really want you to remember this fundamental mental stack. Check the header's authenticity, verify the cryptographic inclusion, and optimize your repeated work. I'll leave you with this final provocative thought. If batch verification requires such incredibly careful bookkeeping, how do modern, complex smart contract platforms restructure their state trees, like using Patricia Tries, to make this aggregation completely seamless for the ultimate light client experience? Now that is where things get truly fascinating. To explore that question, dive deeper into Web3 systems and find more explainers like this one to fuel your curiosity. Visit forge.college today. Thank you so much for joining me, and keep exploring.